Let me start by thanking Kai for the invitation to contribute to this virtual Axion Institute. I'll be talking about structure formation limits on axion-like dark matter, which is based on this paper here that appeared on the archive toward the end of last year, and now it's accepted for publication in JCAP. The work is done in collaboration with Sven Baumholzer and Enrico Morgante from University of Mainz. In this slide, I'm just showing general situation for the axion-like particle constraints from Astrophysics and Cosmology. For instance, here in blue, you can see the limit from the horizontal branch stars, essentially from the cooling, and also here the supernova cooling limits. Whereas most of the other limits are just connected to the cosmology. For instance, there are CMB limits and also a couple of bounds associated to the BBN. Our work on the structure formation limits on ALPs essentially adds to this plot in this lower left region here. Let me start with the model, and also I'll discuss motivation on this slide. So the Lagrangian contains axion, which is the dynamical degree of freedom, hence kinetic term, and the mass term. These two terms are followed by three terms for fermions and photons that are just appearing also in the standard model. And finally, we have ALP interaction with photons given here, this AFF tilde term, as well as the interaction with fermions, that is this derivative coupling. These two couplings and the ALP interaction with fermions and photons can be connected to recent hints from the experiments for the new physics. For instance, we know from 2014 the excess at around 3.5 keV line. One can in principle interpret this as 7 keV axion decaying into gamma lines. And that was done, for instance, in this paper by Jekyll, where they used this kind of coupling here. Also, this kind of coupling was recently used in several papers, including the original Xenon paper, as well as, for instance, I quote here a paper on relaxion by my collaborator, where the excess of the electroempirical events in Xenon 1 ton was tried to be explained. So one can also use, for instance, axion interactions with fermions to get additional contribution on that. Let me proceed by just showing the Feynman diagrams for the dark matter production. Before discussing the structure formation limits, we should emphasize how the dark matter is produced here. These are the diagrams for both photophilic case, so for the case where axion talks to photons, and for the photophobic case where the couplings to fermions is only there. So in the first row here, there are the diagrams for the scattering. So this is for photophilic and photophobic. And the second row contains the diagrams for the fermion annihilation as far as the ALP production is concerned. So with this kind of interaction, one can immediately think about freeze out, but it is known from, it is known that the KV dark matter cannot be frozen out with correct relic abundance. If you look at this part of the expression here, it's basically telling you that you would be overclose the universe unless the number of degrees of freedom is so large that gets compensated. But that kind of scenarios are of course not of our interest. So therefore, we're turned toward the models of freezing. And we explain the dark matter abundance using that model. In the freezing, there's, in this estimate for the abundance, there's this extra factor of interaction rate over Hubble, and that is always smaller than 1 because the ALP never thermalizes. So I should point out for photophobic case that using the equations of motions, the derivative coupling to fermions from the previous slide can be now re-expressed in terms of as this in this form, which means that the couplings is essentially proportional to the fermion mass. And given this kind of expression, it is straightforward to infer that for the photophobic case, the dark matter production rate wouldn't be suppressed with respect to the photophilic case by this ratio of the fermion mass to reheating temperature. So in other words, if you have both couplings to photons and fermions present at the same time with a similar Wilson coefficients, the photon case would dominate and the phenomenology would be driven by that term. And that's the essential reason why we're studying the photophilic and photophobic case here separately. I should also point out that for photophilic case, we'll be interested in temperatures, reheating temperatures around 10 to 15 GeV and smaller, whereas for photophobic case, we are interested in the complementary case, where the reheating temperatures are below the electroweak symmetry breaking, in particular in scenarios where the top quark is Boltzmann suppressed and does not contribute, and the fermions to which ALP couples are essentially charm, bottom, and tau, whereas the lighter fermions are just, their mass is just too small to significantly contribute. The first step toward calculating the structure formation limits is to inferring the ALP dark matter distribution function. And that's done by solving this kind of Boltzmann equation. On the left side, these are the evolution terms. And here is the collision term that contains all this particle physics information that was there in the last slide. So if one assumes the particles in the bath to follow the Maxwell-Boltzmann statistics, one can express the ALP dark matter distribution function like this. And even these further two integrals can be solved analytically. So for that case of Maxwell-Boltzmann statistics, we can fully analytically obtain the expressions for the distribution functions. So that kind of, the distribution functions are shown in this plot here, where I can point out, for the moment, we can look at the blue and the red curves. The blue ones stand for the photophilic case, assuming Maxwell-Boltzmann statistics, and the green one is for photophobic, also for Maxwell-Boltzmann statistics, which is here, the curves are appropriately rescaled with the ratio of reheating temperature and the mass, such that they can actually be shown against photophilic in the same plot. So the dashed curves are for fermion annihilation and the dot dashed are for fermion scattering. And given these curves, I can also proceed with the further integration and obtain the expression for the relic abundance. So you can see that reheating temperatures around 10 to the 15 GeV for the ALP mass of 10 keV produce the relic abundance, correct relic abundance, if the ratio of Wilson coefficient and the ALP decay constant is around 10 to the minus 17 GeV. So I should point out that the contributions for photophilic case between fermion annihilation and scattering, they're roughly 1 to 20, so they're ordered or magnitude apart, because the one from scattering features logarithmic enhancement coming from the regularization of the diagrams, one of the diagrams for the ALP production. That's the diagram that was there on the previous slide, essentially the T-channel exchange of a photon. And we do this regularization by introducing the thermal mass. For the case of photophobic, I should point out also that both contribution from fermion scattering and annihilation give a contribution of similar size. Their difference is only a factor of 2. In case you didn't notice from the previous slide, I'm repeating this plot and want to stress that there is a certain break in the dot dashed curve for the case of photophilic. And this is coming from the fact that this kind of treatment of the regularization of the diagram still leads to the occurrence of the negative momentum distribution function at very low momenta. That is, of course, unphysical, which means that there should, in principle, be it should be possible to improve this kind of calculation. Before discussing the quantum mechanical approach that we also performed, I should point out that this break is happening at the values of momenta over temperature, which are roughly 2 orders of magnitude smaller than the mean values of average moment over temperature, which means that this kind of break does not really impact in any way the structure formation limits that we're about to derive. We also analytically infer the location for this break, and it is here, as you can see here, given here both for standard model case and QED with only one fermion, where there's also such a break, but it's a different location, and location is governed by the thermal photon mass, which is different in those two models. So as I said, this is not super crucial for our calculations, but we still wanted to dig a bit deeper, and we performed also the momentum distribution function calculation using the quantum approach from Boltz et al. So we take the quantum statistics, and what is probably more crucial is to emphasize that we take a different strategy for regularizing the IR divergent diagram. In particular, the term that is regularizing the divergence is extracted from the ALP self-energy contribution, which is computed with the resummed photon, with the fully resummed photon propagator. Unfortunately, we found that in that procedure, and this is given here, the corresponding results for quantum statistics are given here in black. There's still a break, and essentially the break is at the position of characteristic coupling times the temperature, which means that at smaller values of momenta, there is still missing. And what is missing essentially is the full calculation in the thermal field theory. In other words, the photon ALP vertex should also be resummed. It should be thermally corrected as well as the ALP self-energy contribution. So we leave that kind of calculation was done previously for the case of thermal ALP, and we leave that study for future for the case of freezing ALP. And for the moment, we proceed with the calculation of structure formation limits, assuming the Maxwell-Boltzmann statistics, which is here more convenient, and because all the results are analytical. We also checked that the average P over T in case of both Maxwell-Boltzmann and quantum differ by less than 1%. So it's essentially irrelevant which of these two calculations we proceed. Finally, for the photophilic case, we find the dark matter to be slightly warmer. That will mean that the limits will be stronger, and that will be apparent in one of the next slides. So how do we proceed? Just generally, the warm dark matter can wash out structures at small scales, and this is usually quantified by the suppression of the matter power spectrum, denoted by P. It's a function of K, which is an inverse scale, simply because the matter power spectrum, that's a correlation function of the Fourier transform of the deviation of the spatial matter density with respect to the averaged values. So for the structure formation probes, we can consider two cases, the Lyman-alpha, two data sets. One is Lyman-alpha forest, and one is the number of the observed Milky Way subhalos. So the Lyman-alpha forest occur from the spectra of distant quasars and galaxy clusters, which are at higher redshifts. They're emitting photons, but those photons can be absorbed by the hydrogen in the intergalactic medium, and that medium would be at smaller redshifts with respect to those quasars. So in the spectra, in the final spectra, there would be essentially a blue shift. There would be lines at smaller wavelengths, and those are essentially standing for these Lyman-alpha forests. The usual strategy is to define a transfer function T, and we compute it using a class that is a well-known cosmological code. Transfer function is nothing more but the square root of the ratio of the matter power spectrum for the ALPs and standard model contribution. The lambda CDM contribution. And given that, we can make a comparison to the analytical fit of the transfer function for a warm thermal relic. The reason why we compare to the warm thermal relic is because the cosmological surveys are usually giving the limits in terms of that kind of dark matter. So mass of thermal relic enters in this kind of expression here through the coefficient alpha, and I should also stress that this nu power nu is very close to 1. It's a number very close to 1. So in a nutshell, we perform a half mode analysis and define the scale k1/2 at which the transfer function squared drops to values of value of 1/2. At that point, we just check whether transfer function squared is greater or smaller than this reference analytical fit. And if that's not the case, the tested point is disfavored. The analytical fit, for instance, in this plot, we show for two different values, 1.9 and 5.58 keV. This is simply because the results from the observation are usually reported. We found papers which are reporting values for the constraints in this range. So just we can have a look, for instance, at ALP with mass of 1 keV. You can see that it's excluded using this half mode analysis method, both using this 1.9 or 5.58 of mass of thermal relic as a constraint, because this dashed blue line is not above this analytical fits for all the parameters below the k1/2. If you take a look at the ALP mass of 10 keV, which is given here, you can see that this more aggressive limit of 5.58 thermal relic would be disfavoring it, but the less aggressive 1.9 would not. So when we show the limits later, we will essentially report both aggressive and conservative limits depending on which of these two numbers is employed as a comparison. As far as the number of Milky Way companions is concerned, we conservatively estimated that to be 64, and if our ALP dark matter has a prediction for less than that, such mass is excluded. Here's the expression for the number of subhalos. You can see explicitly that matter power spectrum enters explicitly here in the calculation, and also it also enters here. Interval of the power spectrum is this S. As you decrease the mass of ALP, both this numerator and this variance in the denominator would go down, but the numerator would go down at a higher rate. So therefore, there's a stronger, there's a bigger strength to disfavor ALP masses which are smaller. What also enters here in the calculation is the mass of the host halo, the Milky Way. And its mass is still not perfectly known. The most precise measurements are from Gaia. And we take the numbers, Milky Way between the masses of 10 to the 12 solar masses and 1.5 times 10 to the 12. And similarly, as for the case of Lyman-alpha constraints, here we will also report conservative and aggressive limits, depending on which of these two numbers is employed in the analysis. So I can already show the results. Here in the table, there is the conservative and aggressive limits for Lyman-alpha and Milky Way subhalo counts. And you can see that the conservative limits are around 5 keV, but the aggressive can go up to almost 20. Those limits are shown here in the plots as vertical lines and also highlighted with these blue regions. The y-axis is the Wilson coefficient over the ALP decay constant, and the x-axis is the ALP mass. This diagonal line is essentially saying that with the reheating temperature of equal to the Planck mass, the correct relic abundance is here obtained. And here's the corresponding line for 10 to the 14 GeV. So below this line here, you need the reheating temperature above the Planck mass to explain the dark matter, and that's theoretically a bit that's theoretically not super motivated, because at that point the effects from quantum gravity could start playing a role. In this region between Planck mass, reheating temperature of the Planck mass and 10 to the 14, we found that there could be a relevant contribution from misalignment in the production, which would essentially come from the fact that initial misalignment angle cannot be zero, but is fixed by quantum fluctuations. And therefore, given our constraints are based on the model of freezing, we provide in the paper several options how to suppress the contribution from misalignment. One of them is by assuming Peccei-Quinn symmetry getting broken after inflation, and the other one is that if Peccei-Quinn symmetry gets broken during the inflation, we need the axion to be very heavy. Above the 10 to the 14 GeV, the misalignment contribution would in any case not be very relevant. Here you can see that the X-ray limits, which are also shown in this plot here, would die below 2 keV, and at that point our limits would be dominant. One more thing to stress is here the future projection from Vera Rubin observatory. That means that in near future, these limits, which reach now 20 keV, can be improved up to 80 keV, and then at that point, this interplay with X-ray experiments will become even more significant. Speaking about X-ray, it's also interesting to discuss briefly this infamous 3.5 keV line that will be coming from decay of 7 keV axion. That would be around here. As you can see from the table, our conservative limits are fine and not in collision with that kind of explanation, but the aggressive ones are very strongly disfavoring such an option. Here is the result for the case of photophobic. Again, first let me show you the limits. The limits are a bit weaker because the dark matter here is colder, as you could have seen from the expressions and also the shapes for the distribution function. What is also shown here in green are the region where the correct dark matter is obtained, and this line here, the upper edge of this green region, is for the case when ALP talks only to tau leptons, and here the bottom line is where in addition to tau, ALP also interacts with charmed and the bottom quarks. The other flavors are not relevant because, again, as stressed earlier, the top quark contribution at smaller reheating temperature that we consider for this case, the top quark is Boltzmann suppressed and doesn't contribute, and the lighter than charm masses are too small to contribute, because remember that in the photophobic case, the ALP coupling is proportional to the mass of the fermion. What is also visible here in this plot is the constraints from xenon 1 ton and red giants. They're also only relevant if ALP has a flavor universal coupling, because they're derived for the ALP coupling to electrons. So in case the ALP only interacts with these flavors here, those would not hold, but they're essentially saying that they're superimposed with this red region. From this, we can essentially infer that the flavor universal scenario would be partially disfavored here. There's also the X-ray constraints that exist for this photophobic case. So even though we don't directly couple to photon at the Lagrangian level, at the one loop, the coupling to photons gets generated. And we checked that that one is only relevant for the couplings to electrons. So if one considers these heavy flavors only and departs from aforementioned flavor universal coupling, those X-ray limits would not be relevant at all, and therefore they're not even shown in this plot. Again, the Vera Rubin observatory will be able to improve the limits by at least a factor of few. I should also point out that our limits here are also partially excluding the model from my collaborator on real axion that I discussed briefly on the one of the first slides. And this brings me to the summary slide. We studied here ALPs, which are still one of the most popular BSM extensions. They're studied and tested across the scales. We consider keV-scale ALP dark matter, in particular interactions with photons and fermions. And we motivated this by these kind of interactions by previous hints and the experimental findings from both X-rays and dark matter detection experiments. I also outlined the calculation for the ALP momentum distribution function and two different approaches utilizing both Maxwell-Boltzmann and quantum statistics. And also emphasized that in the full model, they could in principle be the momentum distribution function could change sign. This kind of feature does not impact our calculations though. So we used Lyman-alpha forest data and the number of Milky Way subhalos to derive the structure formation limits. And for the photophilic case, we got the limit up to around 20 keV, whereas the colder, more cold dark matter photophobic ALP, there we have a limit of around 15 keV. And those two limits will get improved by a factor of few, provided the data from upcoming Vera Rubin observatory. Then when the limits get improved toward even 50-60 keV, then the interplay with existing extra constraints will be more strong, and the capabilities of probing and hopefully finding dark matter at these keV scales will increase dramatically. So thanks, and if there are any further questions, you can contact me or any of the co-authors.